test. This is a demonstration of the Kruskal-Wallis test. I'm going to use Aqa S3 paper June 2013 question 5 as an example, and let's work our way through it. Okay, what's the question tell us? Firstly, 3 different psychological approaches, 1, 2 and 3, can be used by psychologists for treatment of post-traumatic stress disorder. 16 adults, all of whom suffered a similar traumatic event, were allocated at random to one of 3 psychological approaches. Each adult was assessed following 6 months of treatment and was given a post-traumatic stress score. A higher score indicates a greater level of post-traumatic stress. So high is bad, low is good in terms of a treatment. The scores are here, set out in a table. Data. That's our data that we're going to use for our test. It's going to be our test data. And let's have a look at what the question asked us at this point. Carry out a distribution-free test. So let's quickly look at that. In the exam, if they ask you for a distribution-free test, we've only got 2 choices that are uniquely identifiable. If there were 2 samples, we'd be looking at Mann-Whitney, and if it's 3 or more samples, we can only use a Kruskal-Wallis. So let's write out that our test there, we've got 3 samples. So we are looking at a Kruskal-Wallis test. Kruskal-Wallis test. Okay, if we work that out, let's get on and look at the other data they're asking us for. So this is carrying out a distribution-free test using 5% significance level to investigate whether there is any difference, not greater than or less than, but any difference between the average post-traumatic stress scores for the 3 psychological approaches following 6 months of treatment with a psychologist. So they're asking us just if there's any difference. Okay, so let's go on. Now, hypothesis, we always go to our hypothesis first, and we define our null hypothesis. In a Kruskal-Wallis test, our starting hypothesis is that all samples came from same population. That means that we can rank them and compare them because they're from the same population. Now H1 is going to be the opposite of that, but in a Kruskal-Wallis you actually only need there to be 2 samples that are different. So the H1 is that at least 2 samples came from different populations. So that's pretty quick. There's not a lot of decisions to make in Kruskal-Wallis because you're going one's the same and the other ones they're not all the same, therefore at least 2 are different. Okay, let's have a look at our test statistic. Now in test statistic, all the information on Kruskal-Wallis is in the tables. So here's the reference. You can go to the AQA tables booklet formula, and we're looking at page 14, and it sets out the method for us. So firstly, it sets out what our test statistic is going to be. Test stat, and we're going to calculate this test stat is going to be H, and there's this long formula for it, but we can break it down into the inner part of it is doing this summation here, and then we're going to multiply around it at the end. But this summation is based on TI, and it's given us a definition of TI here. So TI is the sum of the ranks of a sample of size M. So that's summing ranks. We've done this before, haven't we, in the other tests, Wilcoxon, where we ranked the data and then we've summed it up. So we're going to follow that route. So let's go back to our data, our test data, and get to work on that, and we'll do that as the first step. Okay, so we're going to rank this data, and as it's all from the same population, we're going to rank it together. It doesn't matter which sample it's in, we're just going to rank all of the 16 items or scores from lowest to highest. You could go high to low or low to high, and actually it will come out in the wash when you do the calculations later. You'll get the same answer. But I'm going to rank low to high and work my way through and we're really interested in people with low scores. That's a more effective treatment. So the lowest on this is number 1. Is the 7, that's going to be number 1. The second lowest is number 8, and so that's going to be number 2, rank number 2, and the next is 10, which is going to be number 3. But we are ranking all of the data at the same time, so the 4th in the ranking is going to be from the second treatment, that's number 11, and the next one is going to be back to the first treatment, that's number 5 is 12, and our number 6 here in the rankings is going to be the first one in the third treatment. So as you can see here, we're just treating that as one set of data and just going to rank it 1 to 16. I'm just going to add the other numbers in here to do it quickly. Okay, so there are all of the rankings 1 to 16. Next step, as with our Wilcoxon, is we need to start summing these up, and we're going to sum the ranks in each of the methods. So T1, adding up 1 plus 2 plus 3 plus 5 plus 7 plus 9 gives us a total rank of 27. And the number in the sample, there's 1, 2, 3, 4, 5, 6. So the N going with that is there were 6 items in the sample. Next one, T2. If we sum those up for 8, 11, 13, 16, we get 52. And the number in the sample, there were 5 items in the sample. T3, we sum 6, 10, 12, 14, 15, and we get a total of 57. And in the sample, N3, again, it's a sample of 5. Now, we can quickly check that we've done our maths correctly, because if we add our 27 and our 52 and our 57, we get 136. Now that should add up to the same as adding 1 to 2 to plus 3 plus 4 all the way up to plus 16. And we've got a little formula for that, which is that we have to do n plus 1 over 2. That will be the equivalent of that sum. And in this case, that will be 16 times 17 over 2, which is 136. So tick, we've done our calculation correctly, and we can take that information now down and use that in our calculating our test statistic. So let's do our test statistic as quickly as we can here. So our test statistic calc, just copy those numbers in. T1 equals 27, N1 was 6, T2 was 52, N2 was 5, and T3 for the third treatment was 57, and N3 was 5. Okay, so the first thing we're going to do is work out that sum from above, because we need to do all the adding up from our test samples. So that means carry out each of these calculations and add them together. So looking at the first one, T1, we've got to get our 27, that's our TI, we square it, and then we divide it by our NI, which in this case is 6. So that's our first calculation. For the T2, we've got 52 as our TI, we're squaring it, and we're dividing by 5 because that's the N. And finally, for the T3 is 57, so we've squared that, and we've divided it by 5. And if you carry out that calculation with your calculator, you should get that it adds up to 1312.1. So that's our inner calculation there for what we've got in the bracket. Now we've got to go through, carry out the rest of it to find our H. First thing we need is our N value. So as it told us at the far end here, N is adding up all the little n's that we had earlier. So that's our 6 for N1 plus 5 for N2 plus 5 for N3 3, and that gave us 16. So if we now go into calculate RH, so we've got 12 over 16 and 17 multiplied by the 1312.1 we calculated earlier, and then 3 times n plus 1, n plus 1 is 17. So there's our calculation, and that comes to 6.89. Now, for some of you who've had problems in the past, if that number comes out as a negative number, there's something wrong with your calculation. You should go back and check it, because it's always got to be positive. So if you do have a problem, do go and check it. Now, next part of our piece of work is to work out our critical value. And if we quickly go back to what it told us up here on the formula sheet, it says H is approximately distributed as chi-squared. So we're going to use a chi-squared distribution with k minus 1 degrees of freedom, where k is the number of samples. Now here we had 3 samples. Let's go back up and have a quick look. 1, 2 and 3. There are 3 samples, separate samples, yeah? Don't get confused and think there's 16. There are actually 3 separate samples we're comparing. So our k is going to be equal to 3. And so that means our degrees of freedom will be 3 minus 1 equals 2. Okay, so it's told us that it's chi-squared. So we've got a chi-squared distribution. We've got a degrees of freedom, which we'll see in a minute on the table sheet, is called little v, and that's going to be 2. We also need to know what our probability is we're working to, and we need to go back to the question, have a quick look, and what did they set us? They sent us a 5% significance level, yeah? So we've got 5% significance level. Significance level. So if we now have a quick look in the tables, so on page 27 of the tables, table 6 gives us the chi-squared. Now it's important to look at the shape here because we've got to decide what probability we're going to pick. Okay, and as you can see from the diagram, they're giving us the figure from some value, they're giving us the area there as being the figure. We've been told in our question that we've got 5%. So that end is going to be 0.05. So this area here is going to be 0.95. So we're now interested in the 0.95 column. Second thing they told us was our degrees of freedom was going to be k minus 1, which was our 3 samples minus 1 equals 2. So we've now know that's what it's got here in this column here. So we're looking at line 2. So if we look where those two intersect, we end up with our critical value as being 2.991. Okay, I'm going to use this now to create our hi-ho line. It's important that as we're using a chi-squared distribution, switch the back on board, so we know our diagram looks like that in terms of when we're creating our hi-ho line. We're going to have a critical value, which we've worked out just now to be 5.991. And we're interested in something more extreme than that. So there's our critical value, 5.991. We're interested in this end. That's more and more extreme, and it's further and further away from the norm. So that's going to be our high area, and that's going to be our ho. So in effect, in these cases, we have a ho-high line. But the reason is when you look at the shape down on the bottom right, when you look at the shape of the chi-squared distribution, the most extreme area is off to the right, where our number gets very big. We've also already worked out what our t value was, so our test statistic value was. That was our h, and it was 6.89. So if we put that in the right place here and mark it up, it's at 6.89. That's our test statistic. So as we can see, we're in our high area. It's important that we write down that the test statistic is greater than the critical value, and therefore, as we're in the high area, then H0 is rejected. So we've now completed the first part of our test, and we've proved that our H0 is rejected. We now need to complete our context statement. Now, in Kruskal-Wallis, our context statement is pretty structured, given the way it works. So firstly, as we know that we've rejected H0, we know that there is significant evidence that. So that's our standard bit that we're going to write for any case where H0 is rejected. There is significant evidence that. And because we go back to our H1 that we had earlier, our H1, let's just quickly read that, at least 2 samples came from different populations. So we're just going to copy that back down. That at least 2 samples came from different populations. So that's pretty generic, isn't it? There's not a lot of specific in there because at this point we don't know necessarily which of those come from different populations. But let's go on, because quite often in these cases they ask you a second question that takes you into that. So let's have a read of part B. Pamela, a psychologist, wishes to reduce as far as possible the post-traumatic stress scores of adults following their treatment. Recommend giving a reason, your choice of which of the 3 approaches you would advise Pamela to use. So they're asking us to pick from those 3, and we need to use data we've already calculated, and the fact that what we're looking for is to reduce the stress score. That's important because we need to have that. We're looking for therefore the one with the lowest rankings, because what we've got from the data we got earlier is we actually know what the rankings are for the different treatments, and what we're interested in is the ranking is effectively going to show us which is the lowest. So if you've got a lower ranking, you've got on average a lower stress score. So if we look at the first one here, we had T1 had a combined sum ranking of 26, and there were N in the sample. In T2 we had 52 and N2 was 5 in the sample, and T3 was 58, sorry, correction 57, with N3 equals 5. So for each one, what we want to do is find out what the average stress score was. So we're going to do that ranking. So we're going to do T1 over N1, which in this case 27 over 6 is going to give you 4.5. T2 over N2 is going to give you 52 over 5, which with the calculator you'll find is 10.4. And T3 over N3 in your calculator, 57 over 5 is 11.4. Okay, so we can see here that T1 has a significantly lower average ranking. So that means that it's got a lower, and because we matched that to stress scores, it's got a lower stress score. So we would recommend using treatment 1. So there's your point for choosing treatment 1, and the reason for that is that it has a lower average stress score. And if you've done the calculation above, they can see how you got that. So that's answered that one. I think you got 2 points for that, didn't you? 2 points for answering that question. So if you feel comfortable, go and do it. If you don't, just finish at that point. And finally, for you to keep and write down in your notes this is my little summary of the whole of the Kruskal-Wallis test and the 5 points that you have to have on board, or 6 points and the shape. So thank you for listening and hope that's useful.